we were discussing equivalence relations, subsequently something called equivalence classes, and towards the end of the last lecture we saw that counting the number of different equivalence relations and counting the number of ways of partitioning the underlying set, they are one and the same, and that link we got it via equivalence classes. For example, if A is say 1, 2, 3 and we are interested in counting number of different equivalence relations, so which means one relation is 1, 1, 2, 2, 3, 3, and second relation is along with 1, 1, 2, 2, 3, 3, we may have say 1, 2, 1, 2, 1. So like this one can start listing them, and we saw that for this, if you look at the underlying equivalence classes, equivalence class of 1 contains 1 alone, equivalence class of 2 as just 2, equivalence class of 3 as just 3. And in some sense, the set of equivalence classes corresponding to this relation gives you a partition of the underlying set 1, 2, 3. If you look at this, the equivalence class of 1 as 1 and 2, the equivalence class of 2 as 1 and 2, equivalence class of 3 as just 3. If you look at the set of equivalence classes, then we get this. This is also a partition of the underlying set. So counting the number of different equivalence classes is equivalent to counting number of ways of partitioning the underlying set, which we got it via the equivalence classes. In general, we are given a set of n elements, say 1, 2, 3, so on up to n. We are interested in knowing number of different equivalence relations. Equivalently, number of ways of partitioning the underlying set A. We shall now count this via an interesting recurrence relations. Please pay attention. You take an arbitrary partition of A. So P1 represents some arbitrary partition of the set A. That could be this, or it could even be 1, 2, 3, or it could be 1, 2, 3. So it could be anything. So if you look at that arbitrary partition, so you will have some elements in, say, this, let me call it as A1, this let me call it as A2. So like that, some number of subsets will be there, say k of them. So this may represent just 1, this may represent 2, this may represent 3, or this may represent 1, 2, 3 and all these are null, or this may represent 1 and this may represent 2, 3. Okay, so it could be any partition of the underlying set A. If you look at this arbitrary partition, so somewhere you have A1, you have A2 and say AK. So somewhere the element n appears. Assume, because it's a partition, one cannot leave any element in A when we look at the partition. So assume n belongs to some partition, say AI. So you focus on AI. So which means if you look at the partition, arbitrary partition, this will have A1 to AI minus 1, then AI, then AI plus 1, so on up to AK. And in this you find that n appears. This could be just 1, this could be say 2, 3, this could be 10, 11, this could be 10, 11, n is also present. So this could be n minus 1, 2, and like that. There are so many partitions, how many? K of them. And in that, in one of them, you see that the element n appears. I am focusing on that subset now. Fine. So we are taking an arbitrary partition. We do not know how many elements are present in each of them, and number of such subsets also we don't know. So we assume there are k of them, and in one of them the element n appears. Because it's a partition, each element appears in some subset. Okay, so n appears in some subset. Let me assume it appears in AI, and towards its left you have A1 to AI minus 1, towards right you have AI plus 1, so on up to AK. Now focusing on this, let us count how many different equivalence relations one can generate, or how many different partitions one can generate, and or how many different ways of listing all possible equivalence classes, and they are all isomorphic to one another, and we will count them via this model or representation. So when we focus on AI, so in general it may be something like this. So this will have say 1, 2, this is A1, and my A2 contains say 3, n, and A3 as say 4, 5, n minus 1, like that it goes. Okay, let's assume n is say 20 and so on. So now this is my AI, because n is part of this. So apart from n, there are other elements. How many? In general we don't know. This could be just 1, or it could even be like this. It could be 1, 2, and maybe n, and it could be 3, 4, it could be 5, n minus 1, and so on. So it may be just one element, which is n itself, and there are no other elements. Okay. So let's assume the cardinality of AI minus the element n is say L. Apart from this, how many elements are there? It could be 0, in this case it is 0. It could be 1, in this case. Apart from n, there are L elements. The value of L is 1 in this case. Apart from n, there are L elements. In this case it is 0. So the possible values for L are, it could be 0, it could be 1, and it may be the case that if the partition is say like this, 1, 2, so on up to n, then all other elements are present here, whose cardinality is n minus 1, which means the maximum value of L is n minus 1. L can take 0, or it can take 1, or it can take all the way up to n minus 1. So the range of L is from 0 to n minus 1. Fine. So we don't know what values that this set can take, and excluding n, which we say an integer L. It could be 0, it could be 1, and so on up to n minus 1. Okay. Now, there are n minus 1 elements apart from n. In that, we choose L. That goes into the set, the subset AI. So, apart from n, there are L elements. So, the possible values are 0 to n minus 1. Okay, so it is n minus 1 choose L. That goes into AI. And once we place L elements into this, what about the remaining elements? Remaining elements are n minus 1 minus L. Correct? And you place L elements into AI, and you are left with n minus 1 minus L. Okay. Let me represent the number of different equivalence relations using this notation Bn. It's a Bell number. So what it says is are number of ways of partitioning the set containing n elements. How are we counting this? So this represents number of ways of partitioning the set A such that cardinality of A is n. So take an arbitrary partition. In that, focus on AI. AI is one which has the element n in it. Apart from this, there will be some number of elements. Let me call it as L. And where can they come from? They can come from this range 0 to n minus 1. So which means it is n minus 1 choose L. It could be 0, it could be 1, so on up to n minus 1. So once you fix this, and the other elements can be partitioned in all possible ways. And how many such partitions are possible? It is B n minus 1 minus L. For example, suppose you have 1, 2, say 3, 4. Let's assume n is 4. Okay. Now, my value of L in this case is 1. Rest of the elements can be partitioned in all possible ways, meaning one can get 1, 2, 3, 4 or 1, 2, 3, 4. And how many different partitions are possible? If there are n elements, then it is Bn. And if there are n minus 1 minus L elements, then it is B n minus 1 minus L partitions. So that is the beauty of the recurrence relations. Recurrence, reoccurrence. You express the function B as a function of n itself, meaning some smaller values of n. N is represented in terms of smaller values of n. In this case, it is n minus 1 minus L. Fine. And now you see that L as a range. The possible values for L are 0 to n minus 1. So for each of them, suppose L takes the value 0, then you get n minus 1 choose 0. Then you look at how many different ways you can partition B n minus 1 minus 0. and that is one count, and take L is equal to 1. Then n minus 1 choose 1 and b n minus 1 minus 1. That is another count. So one has to sum up all of that to get bn. Fine. This is precisely the Bell number, which represents the number of different ways of partitioning A equivalently, number of different equivalence relations, or number of ways of listing all possible equivalence classes. Fine. So let me repeat this part again. We are fixing a subset which has n in it. Apart from that, there are L elements. So the possible values for L are 0 to n minus 1. So n minus 1 choose L, and other elements can be partitioned in all possible ways. So it is B n minus 1 minus L. Now L has a range. Depending upon the value it takes, you get that many number of partitions contributed by this expression. So when L takes the value 0, you get one count. When L takes the value 1, you get one count. And one has to sum up all of that to get Bn. So this is precisely the Bell number. Okay. One can verify for smaller values, which we shall do next. Let's look at a couple of values for Bn. When set is empty, it is vacuously true, meaning it is reflexive, symmetric and transitive. So it is an equivalence relation. There is only one relation. So that itself is an equivalence relation. So number of such relations is just 1. So B0 is 1. When A is 1, number of equivalence relations is also 1, 1 comma 1. The underlying partition, if you see, there is only one way of partitioning. It is precisely this. So B1 is 1. When A is 2, there are two equivalence relations. Subsequently, you get two partitions. One is 1, 2. Another one is 1 comma 2. So there are this many number. So when A is 3, we get 5 of them. For example, this is one partition. Another partition is 1, 2 and 3. So another partition is 1, 3 and 2. Another partition is 2, 3 and 1. Then 1, 2, 3. Okay. So you get 5 of them, which you can always compute via this relation. For example, B3 is n is 3, so which means it is 2c. Possible values for L is 0 and B n minus 1 is 2, 2 minus this thing is B2 plus 2c1 B1 plus 2c2 B0. When L takes the value 2, it is 2c2 B, 2 minus 2 is 0. Now if you plug in 2c0 is 1, value of B2 is 2, 2c1 is 2, value of B1 is 1, plus 2c2 is 1, value of B0 is 1, so we get 5. So now when A is 4, you can generate how many different partitions are possible, or how many different equivalence relations are possible via this number. Fine. And the way we counted this is quite different from the way we counted number of reflexive relations, number of antisymmetric relations and so on. There we were getting a direct count. Over here we were getting a count. It is represented using a recurrence relation. the function n is represented using smaller values of n, and it's not a direct counting as well. We have to model this via something called partitioning of the underlying set. Through that we were able to count. For that, the equivalence classes, the set of equivalence classes acted as a bridge. So often direct counting may not be possible. This kind of modeling and subsequently doing some indirect counting via recurrence relations, some things like that we come across when we do advanced combinatorics. Combinatorics is a field in mathematics, deals with these kind of counting. And when we look at advanced combinatorics, this is one case study from advanced combinatorics. So we may not count directly, instead we count via recurrence relations, we do modeling, through that we do the counting. One classical case study is counting the number of equivalence classes or equivalence relations or partitions via this counting method.